So now we have the third talk, and as the talk of the session, the lead. So the talk from Dinil Divakaran. He was a senior research principal research scientist at A-Star. It's not here, right? So welcome, Dr. Dinil.
Thanks for the introduction. Hi everyone. Last person or second last person to hold you on Friday evening. Actually, it was a very interesting coincidence to hear from step one. One of the works we recently did in A-Star was to solve CAPTCHAs on the dark web using different agents, and very surprisingly, step three came up at one of the top models. Anyway, so coming back, I work at A-Star. A-Star is a premium public sector IB organization in Singapore, one of the leading organizations. A-Star has a number of research institutes, and I come from the institute, which has been newly formed in July this year. It's called A-Star Institute of Advanced Intelligence and Computing. I really need to look that up. Right. Okay. So in A-Star, these are some of the topics that we work on: network security, phishing, detection, dark web, threat intel gathering, reverse engineering of binaries, and as well as security of AI. And in this talk, the focus on network security. So much of the work that I do and my team does is in this intersection of AI and security. Okay. To start with, why do we need AI-based traffic analysis or modeling for security and privacy, right? Why do we need that? Well, there are two broad categories of problems that you want to look into in network. So one is you want to analyze the traffic to find whether there are malicious communications, anomalies, attacks, and so on. The second is network traffic still is one of those entities that can reveal sensitive information of users. So you can launch privacy attack by analyzing network traffic. Right? Given that the context today is that much of the traffic is encrypted, so you don't have these payloads to analyze, then what you're left with are headers and meta information from traffic, and that's one of the reasons I need AI model. Not sure how many of you have noticed or are from this community, but in the last couple of years, we have seen a number of research works on different foundation models for network traffic. Whether they're necessary, sufficient, good enough, and all is kind of debated, not because of the model itself, but because there are other challenges. So a few challenges that I would like to highlight are: one is data. That if you want to build a good model, you need good data. Simple rule, right? And the openly available network traffic data sets we have certain artifacts that are not good for model training because it will lead to overfitting. Deployability is another challenge. So if you want to deploy it as an in-network solution, then it has to be a very simple model like decision tree. But if you go for a neural network, then there's challenges. But more than that, it's also because if you want to analyze traffic as a sequence of packets, you have to wait for the packets, right? And the third one is explainability. Like your model says the probability is 0.89, it's a malicious traffic. That's not explainability for an analyst that sits at a security operations center and sees hundreds of alerts. So we'll not go into these details. If you're interested, this is a paper that I've published early this year, which explains this. Today's focus is on the fourth challenge, to how to represent traffic. the specific purpose of building good models, right? So this is what we focus on. Before going into the problem itself, so it's good to get an idea about what are the different kinds of tasks that we would want to solve by analyzing the traffic. There's numerous ones. Classically, one is you want to classify network traffic, even if it is encrypted, into different applications. Like today, most of the applications are running on top of HTTP. If you have a DNS running on top of HTTP, you can identify it, because we have encrypted DNS protocols today that runs on top of HTTP. Detecting anomalies, attacks, identifying the IoT devices connected to a network. This is needed for enterprises to track the devices. You might also want to have such a solution when you go to a hotel to see if there are hidden IoT devices. Website fingerprinting, it means to identify the websites the users are visiting. So it's an attack on the user privacy. And so on and so forth. There's new kind of attacks like token inference, I think was a Usenix paper last year or so. Tor day anonymization attack and so on. So these are some of the common tasks in the network space. I have to admit that these are also influenced by my past experience of working on this task for the last couple of decades. So there might be more interesting ones as well. Now, this is focuses on traffic representation. So the question is, what do we mean by that? So if you look into a traffic flow, or look into a typical client server engagement. So let's say you're browsing something and you're getting traffic from a server. Actually, it's not a server, it's a service, and the service is served by a number of servers, and one single browsing session leads to numerous packets. Those packets are actually part of numerous flows, like there's a DNS request and series of HTTP flows that are generated. Even a single browsing session can have tens of such flows. And typically we identify these flows using the file tuple, source and destination IP addresses, source and destination ports, and transfer layer protocol. And logically, this is what we call as a session. Although you can define it much more precisely if you want, but I think you will get an idea, right? So a single browsing session can be seen also as a session that you want to model through using your ML system. So this is a standard IP packet. You can see all the fields. The idea is to showcase what are the features that you want to extract, right? So if the payload is encrypted, then you can extract these features which are readily there on the headers, or also you can extract the meta information like packet size and interval time and so on. You could also aggregate them. Let's say hundreds of packets in a single flow can be aggregated, and then you can get the statistics, right? Like flow duration, average interval time, average packet size, and so on. So when you aggregate it, you're aggregating it at one level. So let's call it at the flow level, right? Before moving further, I just thought to highlight this. Because there are numerous goals that this featured representation of traffic, and sometimes they get it wrong. Not all features should be used as such. For example, if you use IP address for modeling, you end up overfitting because IP addresses are not statically related to any malware, right? They keep changing. In fact, even some of these features that might seem like okay to model, for example, packet size, need to be careful because in some of the openly available data sets, the benign traffic is the internet traffic, which has tens of milliseconds of latency. But the malicious one is generated within the lab in the university, which will have much less latency. So if you use packet latency as a feature where the latency of your two different classes are different, then you're introducing artifact, right? So it's very important to keep this in mind, whether you should use a particular feature or not. In fact, there were also research works that use payload of encrypted traffic as features. So obviously, it's quite random, right? So just to revisit again, so this is a session which user browsers, let's say, and it consists of multiple flows, and we call them multiple flows. And now the question is, how would you train a model that can learn a session? Right? So until the deep learning models emerged, the most common approach was to train different traditional models, let's say a random forest, and then it will eventually learn these features, right? So you need to engineer the features and give it to the model, and then train it over the data. So it required engineering features, and that used to be the thing a decade back. With transformers, we have the capability to take matrices that are huge, which means tens of features and hundreds of packets can be represented by a single matrix that you can feed as a single point for a transformer. So you can learn more, basically. So what we did was, the challenge that we took up was to address a particular gap in the literature, which was the traffic was either modeled as packets or flows, but in general, you need a model that can capture multi-format representation of traffic. And we call this as multi-granular representation. So how is it defined? So let's say there are packets and flows and sessions. I mean, packets are flows and flows are sessions, are part of sessions. So we extract these features, semantic feature extraction. And there are two components of UniNet. One is the T matrix that we call, and the T matrix is, the goal of T matrix is to tokenize the representations and then to do the embedding. So to give a visual explanation, the top one is where how the traffic would be represented in UniNet, which means it can capture both flow and packets, and together they represent the session. And so there are identifiers to mark whether a feature belongs to a flow or a feature belongs to a packet. We'll come back to that again. T-Attent is then the modeling, the embedding layer, and then we'll do the multi-class or whatever task that we want to do, like multi-class classification. So what is T matrix? So let's say this is a packet. So it has all the features, port numbers, and so on. Oops, something coming up on the screen, sorry. There's this, okay, it doesn't come here. Fine, I'll just continue. Although I'm not able to, there's a, yeah, can you come and check? Thanks. I think it's fine. I managed to minimize it. There's a zoom error. Okay, it's fine. Oh, once again. Okay, just yeah. Yeah. Sorry, stuck again. Stuck. Oh, maybe we just today. I can just continue. Also, just go. It's not going. Okay. Okay. Yeah, so that's a packet representation, and the flow consists of multiple packets. Okay. Right. And then the flow can be represented by taking the statistics of all the packets that belong to the flow, right? And then we group or aggregate the flows into a session. So we have multiple representations here, the session, the flows, and the packets. Now, what is T-Attent then? This would be the T matrix that represents the packets and flows. So we embed the features. So if it's a flow, first one is a flow. So you embed the feature of that particular flow. If it's a packet, then you represent the packet. Now, how do you know how does the model know which one is a flow or which one is a packet? So we have the segment embedding. So we indicate that at the segment layer to say that this is first one corresponds to flow 1, the second vector corresponds to packet 1, and that would be of flow 1. So we also do position embedding to say that this is actually a sequence. So a flow is a sequence of packets, and a session is a sequence of flows. Then we have the standard attention layers, encoders, which we train. And we train in an unsupervised way using the MFP head, mask feature prediction. So in this, we mask some of the features so that the model can learn to predict them automatically. Now, once we have these, we have trained the UniNet, then we can have task-specific heads. So what are the different heads we want? So one is the unsupervised one, where or the self-supervised one, where we let the model to understand the characteristics of features by masking different input, like if it's a packet feature or a flow feature. And so it's a randomly selected set of masks, and we train it with different ratios, like from 10 to 40% of masking. So this helps the model to learn the context. Okay, so some between a sequence of packet, one packet is missing, but it will learn that over time. Semi-supervised head is useful for anomaly detection. So if you want to detect anomalies in a traffic, then you model the benign traffic because that's what is given to you. And then you try to learn the decision boundary to detect the anomalies. And for this, we use an autoencoder head, right? Finally, we have the supervised classification head. This is useful for binary classification as well as for multi-class classification. And we use an MLP for that. These are useful for tasks such as IoT device identification, website fingerprinting, and so on. So what we achieve with this is we have a unified traffic representation that can take either packets or flows, and we have a training which can take these and then attach the different heads so that you can get an end-to-end model for specific task. So to showcase the how this shows up in evaluation, we actually did a very comprehensive set of evaluations with 4 specific tasks with different baseline for each of the tasks and multiple data sets. So the different tasks we considered were, one is anomaly detection, which means it's an unsupervised learning, and then you need to detect traffic that deviates from the normal. Attack classification, it's a 2-level classification. One is you do a binary classification to say whether it's attack or normal. And then for the attack itself, you classify them into different categories like brute force, CNC, DDoS, etc. The third one is IoT device identification. This is different from meta classification in the sense that there are tens of devices connected to a network, so the scale is bigger. Website fingerprinting is a privacy attack on the user, so it flips the perspective, and it's also supervised. But now we are again pushing it up further because there are tens of websites you want to track and see whether a user is visiting that, given that a user might also visit thousands of other websites, right? So you have a mix of both. It's a multi-class classification, but we have a huge unknown, right? So I'll not go into all the results, but just focus on website fingerprinting. So what do we have? So website fingerprinting, the main task is to identify that given a user and you're able to monitor the traffic of the user at any network box, then can you identify the websites the user is visiting? So that's the question. Obviously, there's no payload. There are very few features available because you assume that the user can be using a tunnel like VPN outdoor. And who is the attacker in this case is basically a network intermediary, like a compromised network router or state actor who has access to routers of telco and so on. We consider two scenarios. The first one is the closed world. In closed world, your goal is to identify one among n number of websites, and it's really not too big. It's probably like 100, right? 50 to 100. And it's a closed world because you train your model on this 100, you try to identify this 100. It's not really the big challenge. Much more challenging scenario is the open world. So in open world, you have n monitored websites and you have k unmonitored, which is like in thousands. So there are thousands of unmonitored websites, you have not trained on them. So you do not know is the monitored website or not. And then you have a few set of monitored websites. So the goal is, you want to know whether the user is visiting a particular political party or a particular community and then try to profile. And we specifically looked into the latest protocols, QUIC for both browsing as well as for DNS. And we collected traffic from multiple points across the world, I think 4 different locations, 75,000 unique websites, of which 500 are monitored. And we are not using the entire website data set for this, but I think I have the numbers here. Yeah. So we look into a few baselines, TDOQ and TMFW, they're all transformer based, but the second one uses a VIT architecture, and the last one, Auto W website fingerprinting, it's based on LSTM. Yeah, so we use the 100 top QUIC enabled domains, and for each of them we have like 360 traces, and then for the unmonitored we have like 45,000 websites. Right? So we obviously make sure that there's no overlap in the training and testing. And this is how the results look like. So in cybersecurity, it's very important to know what is performance and extremely low false positivity. So you really focus on condition -3, which means your false positivity is 1 in 1,000. And at that vertical, you see the performance difference of UniNet versus the next best. It's around 20% difference, even though both are using transformer model. Right? So that's an basically what we take away from this is having that multi-granular modularity gives richer information to the model so that it can learn more between the protocols as well, right? Yeah. Yeah. So to conclude, yeah, this is a work which focuses on representing traffic in a most generic way possible. And it works on packet flows and sessions. In the paper, we show numerous results where sometimes you have only packets, sometimes you have only flows, sometimes you have lossy packets, and so on. Please refer to it if you're interested. And the architecture itself is quite lightweight with just trainable heads that you can attach or can even have adapters. So in future, we want to consider explainability as a challenge. I think it should go beyond the model and beyond the features, as we discussed before. Robustness to adversarial attacks is another important direction that we haven't studied, which means if attackers are aware that there's this model that is used for anomaly detection or even privacy intrusion, how do you overcome an adversarial attack? Who manipulates the traffic accordingly, right? This is one real challenge. Like most of the works in the literature, including our work, is not adapted to real-time streaming data. So how do you adapt to real-time streaming? I think it's very important if you look into analyzing, especially those traffic that go through tunnels, because Tor, for example, introduces its own high latency. Yeah, so maybe this input representation is a good framework for foundation model, but someone has to take it up. Yeah, that's about it.
Okay, thanks for the speaker. So although we when speaker and still use over the time, due to time limitation, so yeah, let's thanks the speaker again. So if you could session with that, that's one more session after that. Okay, thank you.
Thank you. I just wanted to highlight if there are PhD students here, there are some opportunities at A-Star for PhD students who are outside of Singapore. It's called A-Star Research Attachment Program. Just you can search this online and you'll find details.
Okay, yeah, and are you using that? So we come to the last session. Yeah.